Okay, a large proportion of students who attend select entry high schools in Melbourne commute to school via public transport. The commute time of a select entry high school student can be modelled by a normal distribution with a mean and standard deviation. 20% of the time, selective entry students take longer than 50 minutes to get to school, while 37% of the time they take less than 36 minutes. Find the mean and standard deviation of the commute times in select entry high school students. Give your answer correct to 2 decimal places. Okay, so what we're going to need to do here is we're going to need to do a standardized normal distribution. We're going to make a transformation essentially. So we know that the standardized normal distribution has a mean of 0. This is our mean, and a standard deviation of 1. So 1 to the positive 1 to the right, negative 1 to the left. We know that on the actual curve, we don't know the mean. We want to know what the mean is. But we know that 20% of the time, select entry students take more than 50 minutes. So 20% of the time, this area here is 20%. So this is equal to 0.2. Remember, it's a probability density function. So the area underneath it is all adds up to 1. And 37% of the time, so the area is a little bit bigger. 37% of the time, they take less than 36 minutes. So 36 is here. The area underneath here is 0.37. Okay, what we need to do is we need to do a z-score transformation. So what that means is our z-score is equal to x minus our mean over our standard deviation. You can think of this does not come out of nowhere. We're saying if we're to standardize things, so to get a z-score, we take our mean score, we take away the mean. Start that again. We take our score, we take away the mean. So that tells us how far our score deviates from the mean. Then we divide by the standard deviation. So we divide by the average spread of the data. And so what the effect of that is it tells us a standardized score, which we can then plot on our standardized normal distribution. Okay, so we're going to park this piece of information. We're going to need that in a second. So what we're going to do is we're going to need an inverse normal. So let's deal with the first part of this. It says that we want to know on the standard curve, so on this curve down here, on this curve, when is the area equal to 0.37? So you go to your calculator, your menu, probability, distributions, you want an inverse normal. You want the area to be 0.37. And we're doing a standard normalized distribution. So the mean is 0 and the standard deviation is 1. This gives you negative 0.33. So let me just redraw this a bit better. So this, we want it all to line up, right? Negative 0.33 to 2 decimal places. Okay, and that has the same area underneath it. So that has an area of negative 0.37. Okay, that is an area of 0.37. Okay, the next one's a bit trickier. We need to know, we need this part up here to be 20%. Well, if this is 20%, or 0.2, then all this area up to there, up to that point, must be 80%. So this area here, this area, this area, this area, this area must be 80%. So that's what we're going to do. Because when your calculator does it, it doesn't know, it assumes you're talking from 0 across. So we need to say we need 80% of the area under there. So we go menu, again, probability, distributions, inverse normal. The area is 0.8. The mean and standard deviation are the same. This gives us 0.84. So that is equivalent to 0.2. That has an area of 0.2 underneath it. So what we're going to do is going to put this information in. So Z, we've got 2 bits of information. Z, our Z-score, well, let's do the first one. Maybe I'll do that in green because that's the color we did it in. When I say green, I mean this one over here. Our Z-score turned out to be negative 0.33. And I'll try and use the exact answer our calculator gave me. So I'll just put ... to show that I'm using not the rounded answer. Okay, is equal to our actual value, which is 36, minus our mean. We don't know what the mean was. That's what we want to find out, divided by our standard deviation. That's what we're trying to find out as well. So we're going to solve simultaneous equations, and that is our first equation. Second equation is the other one. Maybe I'll do that in blue. So that's 0.84 is equal to, well, the other score, these matched up. Look, these match up. So that's 50 minus the mean over the standard deviation. Okay, and that's equation 2. And now we're going to solve system of equations. Okay, if you go to menu, algebra, I think. Menu, algebra, yep. 7, solve system of equations. Okay, and then you put those 2 bits of information in, and just call it x and y or whatever, because you can't use mu and standard deviation. You'll get a mean of 41.31 approximately, and you'll get a standard deviation of 16.092. Now, when I put that in, I was lazy and I used these rounded figures. I used that and that rounded. If we wanted to be more precise, which we should be, we would use the actual number that the calculator spits out here. We wouldn't round it. Okay, but let's check if it makes sense. The mean for our actual distribution, the non-standardized distribution, is 41.31. Now that looks good. 36 is here, 50 is up here. Looks pretty good. It's in between them. And the standard deviation is 16. The one standard deviation above the mean is 16. So 41 plus 16 is 57. So it's up here somewhere. That's actually 57 is here somewhere. That's one standard deviation, approximately. Okay. And that's it.